Yeah, it's recording now. Terribly
Okay,
sorry.
no worries, no worries. Yeah, perfect. So, yeah. So I hope everybody can see my screen. So let's start with some typos and confusion which was created because of some problems, some mistakes that I said in the class, and also there was a typo in the lecture notes. So, if you remember, so we wrote a basis for these m's, and we wrote them in terms of the metric and the Kronecker delta, like this. So it turns out that this was the typo in the notes. Uh, so the typo was, initially I had written it with a minus and a plus sign, uh, but conventionally it should be written uh, with a plus here and a minus here. So now it has been corrected, and I updated the notes in the Slack. Actually, this convention doesn't do anything if you pick the wrong convention that I had done in the notes. It At the end of the day, it doesn't matter. And like as you know, physics is invariant under change of convention, so that remains the same. But because you guys will be consulting other references and lecture notes, I thought of correcting it. So that was just a typo. Now, the thing that I said wrong, that's actually quite wrong. So let me address that. So we see that there are two sets of indices here. And this was also a question when last time when I committed the mistake. So I was not being a bit careful. So let me explain these. So there are two sets of indices, rho, sigma, and then indices mu and nu, which are written like up and down. So this rho and sigma, you see, they actually level the generators transformations, which we know are six in number because of the antisymmetry. So they level generators. In other words, you can also that these indices, rho and sigma, are they live in the Lie algebra of the Lorentz group. But the indices mu and nu, they are your space-time indices. Okay. And this is why if you compute, say for example, M01 mu nu, you get a quantity, 4 cross 4 matrix, and then that will be equal to minus of M10 mu comma nu. Okay. So you see the antisymmetry when M rho sigma mu nu is written in this way actually comes from the fact that there are two matrices M01 and M10, and they are minus of each other. Okay. So that's the antisymmetry rho sigma that we argued, and that is reflected in this way. However, this matrix in itself with mu and nu written in this up and down way is like it may or may not be antisymmetric. Okay. In this case, it is not antisymmetric. In some cases, it could be, but that doesn't matter because what matters is the antisymmetry in the rho and sigma index. Okay. And because there were two indices, rho and sigma, exercise 5, which is computing number of independent entries in an antisymmetric matrix, so that number matches. So let's say this is the number, and this is also the number of uh, independent entries in an antisymmetric matrix. They match because an antisymmetric matrix also has two entries, row and column, and here also there are two indices which are antisymmetric. So hence the counting matches. But written in this way, there is a priori no relation between this 4 cross 4 matrix and antisymmetric matrices. It's just that the counting matches. However, there is a way you can get an antisymmetric matrix also. So what you can do is again start with this. Let's call this star 10. And so you take star 10 and then you multiply that equation by, let's say we want to lower an index. So you multiply it with eta mu lambda. So if you multiply with eta mu lambda, this comes down. becomes lambda. And now you will have something like m rho sigma and lambda nu. And this you can write as eta rho nu eta sigma lambda minus eta rho lambda eta sigma nu. Now, when written in this form, you see that again, these are Lie algebra generators, these, and these are space-time indices. But when you write in this way, now lambda and nu are also antisymmetric. Okay, you can clearly see it from the structure here. So now when you bring down one index down, you get m's. Like if you write m01 now in this way with the lambda nu basis, then this will be an antisymmetric matrix. Okay, and the reason should be clear because what we did was we multiplied it with an eta, and eta has this weird signs, right? So +1 -1 -1 and -1. So multiplying with eta can change the index structure, and that's what it does, and it lands you with a antisymmetric matrix. So in this kind of a basis, it's antisymmetric, and that's why we learn an important lesson here that whenever you are doing QFT or dealing with and any theory, and you're dealing with multi-index object like tensors, it's always best to like work with all up or all like let's say there's an arbitrary tensor, so it's best to always work with all up or all down indices. Okay, and then you won't run into any errors. Like be careful with objects which have mixed indices, and that's what confused me last time, and that was the error, but I hope it's clear now, and I've also typed all these things in the notes and updated it on the Slack. Okay, so that's done. Now let's move ahead. So last time we discussed a quantity which was called the stress tensor. Let me go there. Yes. So the quantity we considered space-time translations. And so the translations that we considered were quantities like this, where this epsilon was a constant vector. Now, when we demanded that our action is invariant under this kind of a translation T, then we found the Noether current to be something like this, pi mu del nu phi minus delta mu nu, the Lagrangian, where this pi mu was defined to be this quantity del L by del mu phi. Okay, so we had this quantity which we call the stress tensor. It's also called the energy momentum tensor. And then we said that the conserved charges for this quantity where so as we proved last time, this quantity was conserved, so this current was conserved, and then we can write down a continuity equation for it, and that gives us the conserved charges. So the conserved charges were defined like this, just in the usual way, and from the conservation and also as we saw in the proof of Noether's theorem, we know that this quantity is conserved, which is called the conserved charge. And in this case, we identified the P0 as the energy. So this we call the total energy of your system. And we will see why we called it total energy in today's class. And then we denoted the other guys as momentum. Okay. So these are the components of the momentum. Now, so this means that when we demand that our system or the action is invariant under space-time translations, the conserved charges that we get are in energy and momentum. And the energy corresponds to invariance under time translation, and momentum corresponds to invariance under spatial translations. And this again fits nicely with everything in the Lie algebra Lie group discussion that we discussed, that momentum are generators of translations, and energy is the generator of time translations. Okay. So that's why, like in the group and algebra discussion that we did some time back, so we denoted this as this quantity, and we had argued that this generates infinitesimal translations. And clearly you see that P0 would be like del T, and Pi will be like minus del I. Uh, so this generates time translations, like energy generates time translations, and momentum generates space translation. So it fits nicely with that. So indeed, the conserved charges we get for space-time translations are its generators. Okay. So this is why we have this idea that conserved charges generate infinitesimal symmetry transformations. Okay. So there are, yeah, so we saw this from two point of view, once while discussing the group and algebra case, once when we discussed classical field theory just now. And here I should say a few more. Actually, let's first look at an example. So if we do this for the real scalar field, then we can write down the Lagrangian as the following. Sorry. Yes. And from this, you can compute that T00 is this quantity. And which, as you can see, is positive. The momentum will be given as this. So again, this is given as an exercise. It's very easy to compute. And the spatial components you can get as this. So this is the momentum density. T00 is the energy density. So we call these densities because when we integrate them over the whole volume, we get the relevant total quantity. Okay. So, and we clearly see one nice thing about T00, that this is indeed positive. So that we know that energy of a system should always be lower bounded by 0 or by some value. So that already hints at that we have defined a nice quantity, but we will further argue in today's lecture that this is indeed the energy. Okay. Now, there are one more thing that I should say about the stress tensor, which is important. So you notice that normally in the no other argument, so in the normal no other argument, so which is like the proof that we did, we normally write down conservation equations like this, where J mu was the conserved current. So to some of you, this might be weird that now we got a conserved quantity, uh, which has actually two indices. Okay, so you can raise one of the index up, but which has two indices. Okay, and this might be a bit confusing for some of you. So let me address that. So what are the two indices doing here? And just as we started today's class, we had two different sets of indices. Here also, you see that there are you will see that there will be two different sets of indices, mu and nu. So note that in the proof of Noether's theorem, so for that let's step back a bit. There was a quantity. So when we wrote delta S and there was some integral, I won't write down the details, but it multiplied a quantity, the translation parameter epsilon nu, and then there was del mu t mu nu, like this, right? So from here, let's first note that this index mu, this is acted upon by a space-time derivative del mu. So this implies that this index mu is a space-time index, okay? But now note that the index nu is something that multiplies with which translation you are doing, whether you are doing a time translation if the index is 0, or a space translation if the index is I, and so on and so forth. So this nu, just like we discussed in the Lorentz generator case in the beginning of the class, this levels the different generators in the Lie algebra for translations. Okay. So in some sense, uh, this kind of the argument that in Noether's theorem we get a one index object, that's still true, and that index is this mu, because the other index, the index nu, actually is something that levels the translation generators, and that's why we have three translation generators like P0 and three PIs, one P0 and three PIs. So even though we write it as a two index object, it's somewhat actually a one index object contracted with uh, a generator of the translation. Okay, this one. If you like, because at the end of the day, this was a constant 4 vector. So if you like, you can take this epsilon inside, and you can write this like this, where this will be now a new current J mu. So if you do this kind of a manipulation, you from the Noether argument also you get only one index object. Now, because we are discussing this, let me briefly mention why this way of looking at things is very essential when you want to promote epsilon nu to a space-time dependent function, let's say, which we did in the proof. But as we said, that was just a trick. But so this is not very essential for the class that we're doing on QFT, but we will see an interesting application of thinking in this way. So let's say we do this, and for people who are familiar with GR, we know that we look at space-time dependent matrix and these kind of fields. So this is that setting where you promote this to this quantity. Now let's see what happens. So if you now look at this quantity, so you will get the first term as just acting, the derivative acting on the stress tensor, and then you will get, sorry, and then you will get a term which is like this, and the stress tensor is out of it, okay? Now we know that by Noether's theorem, this quantity is already 0. That's the conservation of stress tensor, okay? So that implies if we demand that this quantity is 0, then we should have this guy going to 0. Okay. So which means we should have this times t mu nu equals 0. Okay. Now, we will see shortly. I should have said that first, but we will see shortly that t mu nu is a symmetric object, okay, in its indices. If when they are completely down or they are completely up. And actually, we already saw that example here. So you see that when we write it this way, like for the scalar field case. So yeah, when we do this for the scalar field case, you can actually show that the t mu nu that you get here is symmetric. Okay. And I will comment more about the symmetric case like in 2 minutes. But for now, let's say that this is an additional property that a stress tensor satisfies. If that's the case, you see that here, because this thing is symmetric, so it means that you should have symmetrization of the lower indices in this derivative also. Okay. Otherwise, as you know that summing symmetric and antisymmetric objects gives you 0. Okay. So if this is the case, then this is 0. So that means you get a symmetric action of derivatives on the epsilons. So it means condition, let's call it star 11, will be satisfied when these space-time dependent vectors with this symmetry are 0. Okay. And if you expand this out, so this just means del mu epsilon nu plus del nu epsilon mu is 0. Okay. And why I was telling you this, because this is the motivation why, there is a way to treat the 2-index stress tensor current also as a 1-index object. From there, we got this. And this, when you take a course in GR, you will see that this is nothing what is called the Killing's equation. And these epsilons are called Killing vectors. Okay, this is just a side aside. No need to understand that the GR aspect of it. But note that if we demand to promote the space-time translations as dependent on space and time, so we are no more talking about a global symmetry, then for stress tensor to be a symmetry and a notion of charge coming out of it, this quantity, this equation should be satisfied for the space-time dependent translations, which are these epsilon nus. Okay. But for the course in QFT, we will just take them to be constant. Okay. Now let me talk about the symmetry of this T mu nu. So as I said, that in the example of a real scalar field, in the example that we looked at the real scalar field, this T mu nu was indeed symmetric, but it might happen that it may not be symmetric. So then there is a procedure that one does to make them symmetric, and the procedure is this, that you define a new object theta mu nu as the old object t mu nu plus derivative of some other guy, so that this gamma rho mu nu is antisymmetric in its first two indices. Okay, so when you interchange rho mu and mu rho, you get a minus sign. And why that is necessary? Because now if you take del mu of this new quantity, so you get del mu, del rho, and then gamma rho mu nu. Now partial derivatives commute, so this is symmetric. And this, as we said by our assumptions, is antisymmetric. So this term just drops up. Okay, this term goes to 0, and hence if this is 0, then that implies this is 0. So this new object is also conserved if the old stress tensor was conserved. And now for the symmetric part, what you can do is you can take theta mu nu and subtract it antisymmetric part minus theta mu nu. That gives you T mu nu minus T nu mu plus del rho gamma rho mu nu minus gamma rho nu mu. Okay. Now, because this is the only restriction that we are demanding on gamma, we can set this to 0 by demanding that this equation holds. Okay. That gamma is chosen such a way that this holds. So choose gamma to satisfy above. So if you do that, you do get a stress tensor theta that is conserved and also that is symmetric. And hence in any QFT, without changing the theory, you can always conserve a symmetric stress tensor. Okay. And that symmetric property was needed in this argument to argue that this derivative acts on the space-time objects in a symmetric way. So that's why it was important to discuss the symmetric properties of stress tensor. So let me again stress this thing about the stress tensor, that it is conserved and it is symmetric. Okay, so these are the two most important properties of the stress tensor. Yes, this is, as someone pointed out in the chat, this procedure has a name. This is called the Bellin-Fante procedure, okay? But that's just a name after a guy who did this. But the main content is this, okay? So you can improve it by something like this. So you can make it symmetric, even though when you derive it from the Noether procedure, it may not be symmetric. Okay. So that's another thing out of the way. So that's something that we had discussed last time. Now let's move on to the Lorentz transformations case. So we saw that translations, so translational symmetry gave us energy and momentum conservation. Okay, so we saw that. Now let's ask what happens when we have rotational symmetry. So for that, let's do the following. Yes, that reminds me that I had, so actually before doing this, I had promised you that I will derive the Noether's theorem in a different way. Because the procedure that we did, it involved promoting the symmetry parameter as a function of space-time. So now we don't want to do that. So let us do it in a different way. And that way will help us to write down the Noether currents for rotational symmetry, okay? So let's recall what we want to prove. So we want to argue that if there is a symmetry transformation, del phi a, denoting it as some xa. Actually, let me write del phi a. Yes, of x is some symmetry transformation xa of f. Then by definition, since this is a symmetry transformation, the action should be invariant, which implies that the Lagrangian L can max change by a total derivative, right? Because then you can drop it by integration by parts, ignoring boundary terms, okay? So if the Lagrangian changes by total derivative, then under the transformation, the action is invariant, right? So now let's see how the Lagrangian changes. So as we know by now very well, that the Lagrangian depends on the derivative of the field and the field itself. So now, so this is again usual procedure that we did. Do the product rule, bring it to this nice form. Plus a total derivative term. Again, this is something we did very carefully last time. So we're just expanding the Lagrangian as functions of fields and its derivatives. So now we know that if the action is invariant, then this is what you can identify as the Euler-Lagrange equation. So that must be satisfied. So we can set that to 0. So we get del mu del L by del mu phi A del phi A. And the action can be invariant only if the Lagrangian changes by a total derivative. Okay, that's the definition of a symmetry f mu of phi A. Okay, so when that happens, then only your action will remain invariant and the transformation that you're looking at will be a symmetry. So this means that you can bring the f to this side and you get a quantity like this. Minus f mu, a function of the fields, as 0. And this object you can define as your Noether current. Okay. So J mu is your Noether current. So you see that whenever you have, so we see that whenever we have a continuous symmetry, that implies we get a conserved current. We get a conserved current, and we have argued that we also get a conserved charge from it. Okay. For instance, in this case, the conserved charge is just the volume integral of the J0 component. Okay. So that gives you the charge. So this is the charge Q. And because the charge is conserved, so you can write down that this is 0. Okay. So that's another way to prove Noether's theorem. And that is very useful when, so you see that this J mu is directly given by this object. But if, let's say, f was 0, the f mu was 0, or in other words, if delta L was 0, then obviously delta S is also 0. Then in that case, so if delta L is 0, then in that case, the current is very easy to be found, which is just this. Okay. Because in this case, the f part is just 0. And so this kind of deriving the Noether's theorem is very useful when the Lagrangian also doesn't change. Not that the action is invariant. The Lagrangian is also invariant. It's not a total derivative. It's just invariant. And for the complex scalar field case, you can write, like you can derive the J mu in this way, and you will get exactly what we had gotten. Because in the complex scalar field case, there you can show that the delta L is indeed 0. So this directly gives you current in the easiest way. Okay. Right. Yes, now I have to tell you something before I forget. Then we will go to the rotational symmetry. Yes. So I have to tell you that we said that whenever we have a continuous symmetry, we get a conserved current, and that gives us a conserved charge. Okay. However, we also discussed discrete symmetries, Like in the real scalar field case, we discussed one discrete symmetry. If phi goes to minus phi, then this Lagrangian was invariant, right? Uh, so this was also a symmetry, but this was discrete. So because this is discrete, there are no infinitesimal version. So that implies no infinitesimal version of this. So no infinitesimal version means no generators from the Lie algebra point of view that we have been seeing many times by now. So that implies no currents. Okay. However, there still is a charge. Okay. Because of the symmetry, there still exists a conserved charge. But there exists a conserved charge. Okay. So this means that we, so for instance, in this case, so if let's say this charge is denoted as Q, then if you act on it with on some objects, then you will either get plus or minus the objects. And the reason is, note that I had said that this symmetry that phi goes to minus phi, this is called a Z2 symmetry, which just has two elements with ordinary multiplication among them. So it means that for this kind of an object, if you write down its representations, then either you will have a plus representation or a minus representation, okay, as its eigenvalues. So there will be quantities which will be charged plus, or there will be quantities which will be charged minus. And that's all you can have here. And as you see that this is a discrete case, so you don't have any current, but you still have a concept of charge. So this is one of the reasons why I said that Noether's theorem only works for symmetries which are continuous, but in nature we also have discrete symmetries like this, and we had also seen discrete space-time symmetries earlier. So which were again Lorentz matrices, like the parity that took uh, t x to minus x, and the time reversal matrix that took t to minus t. So these are discrete space-time symmetries which were not continuous, but they will still have some conserved charges. So that's one thing I need to say why Noether's theorem, though is powerful, it doesn't take into account discrete symmetries. The second thing that it doesn't take into account, and this is also important. So the first thing is discrete symmetries. In this case, it's space-time, but okay. The second thing is Noether's theorem required. So we saw that its proof required equation of motions to be satisfied, right? We also called this thing in last class as on shell. Okay. And in today's proof, we saw that that's exactly the case where we set this quantity to 0. Okay. So that means equation of motions were satisfied. So that was crucial to deriving the Noether current and its conservation. However, let's look at in 2 dimension, 1 plus 1 dimension. So in 1 plus 1 dimension, you can define a current like this, okay? Epsilon mu nu del nu phi, where phi is some real scalar field, okay? Now, what is this epsilon? If you, from your special relativity class, you can remember this is what is called the Levi-Civita symbol, okay? For instance, epsilon 0, 1 is 1, epsilon 0, 1 downstairs is -1, and epsilon 0, 0 is 0, epsilon 1, 1 is 0, and so on, okay? And also, as an exercise, this was actually one of the exercises. You can show that this epsilon is Lorentz invariant. So now let's look at this quantity. Okay. So now let's take the divergence of this. So this is a constant matrix. So what does this become? This. Okay. Now you can see that this is antisymmetric, but this is symmetric because partial derivatives commute. So this is actually 0, but this is 0 identically. Okay. What does it mean to say identically? That it doesn't require anything else. In particular, it doesn't require equation of motions to be satisfied. Okay. So this is what is called an off-shell conservation or an off-shell conserved current. Okay. And again, this bypasses the whole Noether procedure. This doesn't require equation of motions. It in fact doesn't require an action or a Lagrangian. If you see that we just constructed a current and it's 0 just by identity. And you can in fact generalize this to higher to let's say vector fields. Now let's look at 3 plus 1, 1 plus 3 dimensions. Sorry, in my convention it's 1 plus 3. So there you can define a current like this. So now you will have the 4-dimensional Levi-Civita symbol. And now let's generalize to the vector fields. Okay, so let's A sigma is a 4-vector field. Again, this quantity is conserved, right? If you do del mu j mu nu, you get epsilon mu nu rho sigma, del mu del rho a sigma, and mu and rho are antisymmetric here and symmetric here, so that's 0. So this way you can generalize this to higher dimensions, to higher number of fields like vector fields, tensor fields, whatever you like. You can always cook up a current like this, which will be off-shell conserved just by identity. And there's an exercise on about this in the lecture, which will be very illuminating for you. Okay. So you please try to do that exercise. But one thing I just need to tell here, just to like keep you interested in all these things. So this is what in recent times, this is what has been called a one-form symmetry. Okay. For instance, the usual Noether current that we discussed objects like this, which had just one index. Now this has 2 indices. So that's why it's called a one-form symmetry, and this analogously will be called a zero-form symmetry. Okay. So this is your first introduction to something that's a symmetry, but that's beyond the Noether and the ordinary one index thing. So we constructed a 2-index current that is antisymmetric. So recall the way I constructed this guy, J mu nu. It is antisymmetric because of the epsilons mu nu. Okay. And in the truest sense, these both the indices here are space-time indices, unlike the stress tensor. So that's why I discussed that part. But the important difference from the stress tensor is stress tensor was symmetric, this was antisymmetric. Okay. Okay, since this is not a course on symmetry, so we won't talk more about this, but this is just to give you a bit of a idea about what like a one-line summary of what these higher form symmetries are. So these are off-shell conserved currents, which can be found in any arbitrary theories. Even at times in theories, we don't have a Lagrangian, don't require equation of motions. They're just true by identity. Okay. And now when I'm saying this, it might seem very abstract to you, as in what kind of theories are there which support these kind of objects, higher index currents, antisymmetric currents. So for that, there is an exercise in the notes, and also when you do QED, you will notice that you will find a quantity there. And if we have the time later, we might discuss this, but I just want to tell you that this is very real, and this is not something that we are constructing like this. Okay. So with that, now let's move on to the rotational symmetry part. And now we will find the currents using this alternative way of Noether's proof. Okay. So under a rotational under a Lorentz transformation. Okay, so let's say the boosts are also rotations, but in space time. So we know that arbitrary Lorentz transformation we can write like this. Okay, and now if we expand this to first orders, again, as I had told you, all the things that we will do, we will only expand things to first orders. Okay, plus order omega square that we will neglect. So that's a infinitesimal Lorentz transformations. Now from here, you see that you can read off the field transformations as this, right? X nu del mu phi. So that's this piece here. And so the Lagrangian density you can compute the delta L. It translates as this. Okay. And because these are constant parameters, you can take them inside. Okay. So and because the Lagrangian itself is a scalar, so just the way the scalar field transforms, it will transform in a similar way. So you can write it like this. And now let us consider the current. So the current, remember, was defined as del L by del mu phi A, del phi A minus uh, this F mu. Okay. And this F mu was this guy, right? So if you write del mu F mu, so this F mu is this. So if you do that and you substitute from above the field transformations and the transformation of the Lagrangian, so you get something like this. Okay, let me see if I'm indexing it correctly. Yes. Okay. And now you can identify this guy as the stress tensor x nu. Okay. This part, so if you ignore the x nu, the remaining part is just the stress tensor, as we know. And if you want to write this a bit better, we can lower the indices and raise certain things. So we get something like this. Okay. And recall that this is antisymmetric because this is a Lorentz infinitesimal transformation. So this is antisymmetric in rho nu. So this means you can now write down a current J mu rho sigma, which is X rho T mu sigma minus X sigma T mu rho. Okay. So this is the current that we get from here, and using the antisymmetric property of the rho nu indices. So because rho nu is antisymmetric, you see here you will have this thing as antisymmetric rho nu from here. So that gives you this current. Okay. And by Noether, this is conserved. Again, it should be clear that the mu here is the space-time index, and these are that level generators. Okay, and that is also in accordance with the rho nu here that labels the generators, because the antisymmetry is again in the labeling of the generators. So the antisymmetry of this guy, this omega, translates to the antisymmetry of the currents here. Okay, good. Okay, Now we can define conserved charges. So Qij, again in the usual way, will be xit0j minus xjt0i. So recall conserved charges are obtained by putting the space-time index to 0. Okay, what was the space-time index here? Mu. So we set that to 0. That gives you the conserved charge. So this will be one conserved charge. The other conserved charge will be Q0i d3x x0t0i minus xi t00. Okay. So these are components of angular momentum, and we will see right away how to see this. And this is the conserved charge associated with boosts. So the first part doesn't need much to explain because you had rotational symmetry, just like translational symmetry gave conservation of linear momentum. Here we get conservation of angular momentum. Now the second part, and there was a question I remember last time, what are the conserved charges to boost? So let's unpack that. So if we expand this part out, by Noether this is conserved by the equation of motions and Noether procedure. Now this you can write it as T3x T0i plus T D3x del by del T of T0i minus d by dt of d3x xi t00. Okay. So I'm just taking time derivative of this quantity and doing it carefully. And now you can identify that we call the first part, this one as the three momenta, pi, and this part is just dpi by dt. Okay. And then we have this quantity, whatever that is. Okay. Now we can call this quantity like uh, xi times the total energy. Okay. We call this quantity, this and this as the total energy when integrated over the spatial volume. So that's the energy. And that whole thing is 0. Now recall that since linear momentum was conserved, so this is already 0. So that means we get dxi by dt as pi over E, where E is the total energy and pi is the components of momentum. So imagine a system, and if you are in the center of, and this is constant, okay, because this is 0 by space-time translation. So let's say now you are in the center of energy or center of mass frame, and this xi levels the position of your center of mass. So it just says that your center of mass moves at a constant velocity, and the velocity is given by pi over E, where both of them are conserved quantities. Pi are conserved linear momenta, E is conserved energy. So this is just like Newton's first law that if a body is like body maintains its inertia. If it is inertia of rest, it's rest. It's inertia of motion, it's motion. And in this case, this is exactly what these conserved charges they give you. Okay, invariance under boost. So now remember that boosts were something that related two frames by an inertial by a linear transformation where one frame was uniformly moving at a velocity v with respect to another frame. So these two frames are called inertial frames, right? So again, we see that as you know that Newton's laws, they are only applicable in inertial frames. They are not applicable in non-inertial frames. So you see a variant of Newton's law in classical field theory exactly for the boosts, which were like a relation between two inertial frames moving with some velocity v. So that's why you get, if you like, some kind of a Newton's first law here, and as we know, they only apply in inertial frames, and that's why these are conserved charges for the boosts. Okay, I think that's done. Now, now since we wrote down the Lagrangian, now let's quickly discuss the Hamiltonian, and then we will move on to quantization, which is the important part of today's lecture. So note that for the real scalar field, we got the Lagrangian to be this. Right? We can define a canonical momenta, which will again be a field. And in this case, this will just be this. Okay. So phi is the canonical momenta of the field phi. Okay. Now, if we do that, now let's define H. What is H? In classical mechanics, as we do, this is like a Legendre transform of L. Okay. So in this case, this will be phi dot minus L, just generalized to field theory. And if you do that, what you will get is this half pi square plus half del phi square plus half m square phi square. And this is exactly what we had called P0 or the D3x T00. Okay. And as promised, you see that at least in the scalar field case, we could argue that this volume integral indeed was the Legendre transform of the Lagrangian density. So it made sense to call this energy. Okay. So first we saw that this was a positive definite quantity, that this quantity was greater than equal to 0. So it made sense like as an energy density. Now we see that it is indeed the Legendre transform of the Lagrangian density, which we call in classical mechanics as Hamiltonian. So when you integrate it over the, the integrated version of this, yeah, this is just the energy density. Sorry, uh, this is just T00. But now when you integrate this, you get the energy. Okay. Let me remove this here. I hope you get the idea. Yeah. So T00 is the energy density or the Hamiltonian density. When you integrate over space, you get the energy. So we indeed see that at least one of the components of the stress tensor is correctly identified as the energy. Okay. And the momentum part we will see in the quantization case. But it should not take you much to convince yourself that since one we have identified as energy, the other three have to be momenta, because we are in a relativistic theory. And if the time component is energy, the space components better be momenta, right? Good. So that's the Hamiltonian thing. Yes, one thing I need to say here is that look that when we were looking at all the Lagrangian formulation of classical field theory, we always did it in a covariant way. Okay, so for instance, we always wrote equations which involved like these tensor indices. So it didn't involve like del t and these kind of things. So it was manifestly covariant. But note that in order to perform a Legendre transform, we need to define a canonical momenta. So when we do that at this stage, so at this step, we choose a time coordinate del t, and with respect to that, we get this phi dot, and we define pi from that. Okay, this momenta. So a very specific coordinate was chosen when the Hamiltonian formalism we constructed. Okay, so this is like in special relativity, now you are choosing a very particular frame. So hence, in the Hamiltonian formulation, at times some intermediate steps will not be relativistic covariant. Okay, so they may look like not manifestly relativistic or Lorentz invariance or Lorentz covariant. But at the end of the day, when you compute observables, as we will quantize the theory and we will see there, that final answer will be independent of whichever frame or whichever time coordinate you chose here. Okay, so this is some arbitrary time coordinate we chose, but that's why people say that when you do Hamiltonian formulation, you break Lorentz invariance, but we break only at intermediate steps, which we do not measure in a lab, let's say. So physics is still relativistic. It's just that some intermediate steps they break that. And in this particular case, this is exactly the intermediate step of defining the canonical momenta that breaks uh, Lorentz invariance by picking up a particular coordinate. Right. Okay, good. So are there any questions? Because now that marks the end for classical field theory. So we will now go to the quantizing scalar fields. Okay. So I can take like 2 minutes, for 2 minutes, some questions. Let's see in the chat. Under which transformation? Okay, that's a good question. So the Lagrangian is a scalar. So whenever I say scalar, it means under Lorentz transformations. Okay. So yes, so under Lorentz transformation, it's a scalar. So that's why in the Lagrangian, you always contracted indices. You never wrote a Lagrangian like A mu B nu and like this. Okay, so the Lagrangian didn't have any indices. So that means it's a Lorentz scalar. Okay, let's say Poincare transformations, but okay, Lorentz transformations. Yeah, under Lorentz transformation, the Lagrangian is a scalar. Okay, any more questions? I can take a couple more if there are at this moment now. I'll wait for 30 more seconds, otherwise we'll start again, okay? Hmm. Right. J mu sigma rho. Okay, that is a good question. So yes, so you see that the Noether procedure of J mu gave us this quantity, right? This omega rho nu times T mu rho J chi. So let's write this properly here. So we get J mu as minus omega rho nu T rho mu x nu. Okay, that's what we got. So now we we can identify it. So just like this is the symmetry parameter, right? For instance, recall that in the stress tensor case, we had like this, right? So this was the symmetry parameter that generated this associated with the symmetry, and this was the stress tensor. So now you see this quantity, we can write this like this, right? J mu rho nu. Okay, so why I'm writing rho nu separately from mu is because this is antisymmetric with the omega. So the antisymmetry of the omega, the infinitesimal Lorentz generators, translates into the antisymmetry of the Noether currents that you get. So this is what I did. So I just wrote J mu rho nu as this, and then I said that in a basis, this can be written as x rho T mu nu minus x nu T mu rho. Okay, so this is now manifestly antisymmetric. In rho nu, and yeah, that's it. So that's all I did. Yeah, if you, yeah, so but when you contract it with omega rho nu, then you can, so if you contract this with omega rho nu, then this plus gets absorbed here, you get a factor of 2 or something because of the antisymmetry that is built into omega rho nu. So that's why from here to here there is this whole step. Okay. So you can convince yourself that if when you contract, you actually get just one term, this piece. This minus gets absorbed here and you get an extra 2. Okay. Yeah. Okay. So good. That's all the questions for now. Let's continue. Okay. So finally, in today's last hour of the lecture, we will go to quantization. Okay. And sorry, it took us like 5 hours to reach here. It's a quantum field theory course, but we had to develop some classical field theory. Okay. So now recall that in classical mechanics, what we normally have is what is called um, Poisson brackets. Okay, and for people who don't know, don't worry. It's just for completeness I am mentioning. But you would have seen this in your quantum mechanics course at least. So if Qi is the moment position and Pb is the momenta, then this is what Poisson brackets satisfy. And when we quantized this theory, let's say we denote it by Qu as the operation of quantization, then we promoted these objects to operators, right? And we said that this is I h bar delta AB. Let me be careful, AB and AB, okay? Uh, so so this was the process of quantization, and now we learned classical field theory where we promote them to fields. Okay, so we will promote these objects to fields, and then we will go to quantization, this QU map. So what we will have are at the end of the day, we will have operator valued fields. Okay, uh, so we will have operator valued fields. So fields which are defined at every space-time point, but they themselves are built out of operators that satisfy these kind of commutation relations. We will see this explicitly. So this is the procedure that we will do now. And note that that it's always best in the quantization case to work in the Hamiltonian picture. And in the Hamiltonian picture, we saw that we choose a particular time. Okay. So we choose a particular time coordinate. So that's why when we will look at uh, now operators, operator valued fields, which will depend on your space-time points, in particular, let's say, depending on time, then we will impose these kind of commutation relations at equal times. Okay. And there will be an exercise for you. So we will impose at equal times, and there will be an exercise that once you impose at let's say some time t equals t0, let's take it to be 0, then they will hold for any arbitrary time. Okay. So we will see this, and this is why we will impose them at one particular time, and then we will forget about it. And this is why these are called equal time commutators. Okay, equal time commutation relations. And we will see that this is indeed the case. We will you will see this in the scalar field case, and that will be enough to convince yourself that this is indeed the case, and we just impose it at one particular time. Okay. Yes. So with that, now for fields, we want to impose these relations. Okay. So now, because we are working in the Hamiltonian picture, so now we have phi and pi. So pi, as we saw, was the was constructed using this time as canonical moment of phi, and these hats denote them as operators, these hats. But at times I will forget writing the hats, so it will be obvious what do I mean, depending on the context. So let me explicitly write the space-time dependence. So you see the space points can be different, that's okay, but they will be equal time, okay? So just like we did in quantum mechanics, we will impose these relations. So these two are trivial relations, and hence I didn't write them while writing this thing. But you know that QQ and PP, they commute. But the interesting relation is this. Now we will again set H bar to 1, and we will get this non-trivial looking relation, okay? So this is analogous to what you had before as Q hat T, P hat T as I, and I'm setting H bar to 1, okay? So this is the same as that, but just written in terms of fields now. And now let's quantize the theory, okay? So we want to impose these conditions, okay? Let me call them star 12. So we will impose these conditions. So let's look at the example of first a real scalar field, just to warm up. Now recall that a real scalar field, the equation of motion was this, right? M square phi. First equation should be, oh, sorry. Yes, very correct. Yes, it should be phi. Yeah, only the phi and phi, they commute. Mm, the first equation, yes. Yes, thank you. Thanks for pointing out that phi and phi commute, pi and pi commute, space and time, they don't commute, right? Thanks. Thanks for that. So now recall the equation of motion for the massive scalar field, real scalar field, was just this, right? And now we are working in the Hamiltonian picture, so we don't care about relativistic covariance or invariance. So we break it to time and space derivatives. And now we can write a Fourier transform of the field and see what this equation looks like in momentum space. Okay. So for people who are not familiar with Fourier transform, I have written an appendix in my notes. You can have a look. So whenever you have translational invariance, you can write things in plane wave basis, and it's there in the appendix. And the inverse Fourier transform looks like this. And also this is the convention that I will be using for Fourier transform, and also other lecturers will be using this particular convention of Fourier transform. The convention has to do with where do you put this 2 pi. So whether you write all the 2 pi in the momentum space or you distribute among positional momentum. So this is the convention we decided to stick, that we put everything in momentum space. Okay, so now if you take these Fourier transforms and you just plug this equation here and you integrate overall momenta. Can you please explain a bit about what you mean by? Yes. So Rana is asking a question. Can you please explain a bit about what do we mean by quantizing a field? So that's exactly the purpose that we will see now. So I just said up until now that we will impose this commutation relation. We will now see what happens when we impose this commutation relation. Why does it mean that we quantize a field by doing this? So I have not yet said anything about quantizing. I just said that we will impose this commutation relation, which we usually do in quantum mechanics, where we just impose a commutation relation, right? In quantum mechanics, you just impose that QP is IH bar, just I, let's say. So you impose that. Okay. What's the motivation? The motivation is because when we started from single particles to fields, so now we want to quantize fields. So what do we do when we quantize single particles? We impose commutation relations. And then we see as a consequence, what do we get? Now we want to impose commutations on fields, exactly how we did in classical mechanics. For instance, there also, like in the single particle case, you just took this thing as given, right? This commutation relation was given to you. You said, let us impose this commutation relation. Now, one might ask you, what's the motivation behind taking that? Okay. And if you push on this question further, the motivation actually comes from understanding what is called a Poisson bracket. So it turns out that in classical mechanics, when you write down a Poisson bracket between generalized position and generalized momenta, you get an equation like this. Okay. So, and the concept of quantization is essentially translating the Poisson bracket to commutators. Okay. But this step is a very non-trivial step. And if you're asking, why does this work? Then I think that's something that is more or less not like, there are ways to motivate this. You are essentially asking what is a quantum map. Okay. So this, I think, is still an active area of research. But what I am doing here is just what we do from classical mechanics to quantum mechanics, but in terms of fields. Okay. So the motivation, if you want, for this lecture, it's this, that there's a Poisson bracket structure, and that translates into commutators. That's it. But what exactly is this map is the question, that what is quantization, which I'm not going to answer because it's something that's very involved and not very easily understandable. But okay, so the idea is that we will impose commutation relations. Okay, and that's what has been told as quantization. Okay. But we can talk more about this later, but yeah, not in the lecture. Okay, so now if we take the momentum space version of this field and we substitute it in the equation of motion, you can show that you get an equation like this for the momentum modes. Okay, this is 0. And this is clear because you see this delta, this Laplacian, this acts on this k, and this brings out terms like ik times ik. Okay, and that gives you minus k square. So that minus then turns this minus as to plus, and you get quantity like this. Now, if you define omega k, a quantity, as k square plus m square, then you see that you get something like the equation of a harmonic oscillator. Okay, so this is exactly the equation of a harmonic oscillator for every momentum mode k. Okay, so now recall that when we started with the scalar field last time, we said that the scalar field Lagrangian describes a set of decoupled simple harmonic oscillators, and that's what exactly we get here. So we get a set of simple harmonic oscillators, but when we will quantize this, you will see that if you have different momenta mode, for instance, if A is level the annihilation operators, then these will be 0. Yeah, so this implies that for different momentum modes, they have their own set of oscillators, their own set of simple harmonic oscillators and annihilators and creator operators. So they are not talking to each other. Like each Fourier mode is decoupled. Okay. So this is why the massive scalar field actually describes infinite set of simple harmonic oscillators, but all decoupled in the momentum space. For each mode, it's an independent oscillator. For every other mode, it's an independent oscillator. They all have their own different set of equations, right? Good. Uh, Okay. Now let's move on. There's some question in the chat, but I'll discuss that later. Okay, let's move on. So this is that part where we explain that this is actually a simple harmonic oscillator in disguise. Now, one thing to note is that in this exercise, we took a quadratic potential, and as you know, quadratic potentials indeed give you simple harmonic oscillator, because that's the differential equation for that. But in general, in nature, you could have terms which are like on top of this cubic or quartic and so on and so forth. Obviously, you want to respect the symmetry. For instance, you cannot have phi cube if you demand Z2 symmetry, like phi going to minus phi. But you can definitely have higher order even terms. So we will not be considering those here. And they will be the next set of lectures when you will discuss interacting quantum field theory. Okay. So now this is all what goes under the name of free quantum field theory, which means that at max your V is quadratic. Okay. But this is a good exercise. Why? Because any potential that you write down about its minima is essentially, so let's say you write down a potential. So, and phi naught is the minima. So the first non-trivial piece is actually quadratic, you see. Okay. So and then there are higher order pieces. So the first, so this is 0 because it's a minima, phi naught is a minima. And the first thing that you get at leading order, it's a quadratic. So that's why we are learning the leading order piece now, and the higher order pieces, which will give you interesting interactions, you will learn in the later set of lectures. Yes, we will discuss all about creation and annihilation just in a little bit, okay? Yeah. So I get there are many questions when I just said that these are the commutation relations, but now we will explicitly see what does this mean? How does this translate to your knowledge of simple harmonic oscillators? So now let's, for the case of quantization, we will not quantize the real scalar field, we will quantize the complex scalar field. And the real scalar field, which is a bit easier, will be your exercise. Okay. So complex scalar field will give us more like mileage. So we will do that. Okay. So now let's, just like in the language of simple harmonic oscillators, we know that this is what we showed, that this is the wave equation satisfied by phi tilde equals 0 with omega k given as k square plus m square. Now we can write down a basis phi tilde, and this I am not deriving, I am just writing it from your knowledge of simple harmonic oscillators. So you can write it in plane wave basis like this: b star e to the power plus I omega k t. Okay. So A and B are different oscillators, and you can expand in terms of this plane wave basis. Now, if we translate this to position space, x and t, okay, then we just multiply by the momentum space integral, and this remains the same. Okay, so I will drop the k at times in the omegas, but let me keep it as far as I can. B star k e to the power I omega k t, and then e to the power I k dot x. Okay, so that's when you write the field in the momentums in the position space. Now see that, sorry, there was a minus here. So at this point, this is something like a notation. But now what I will do is I will relabel k to minus k. And you can show that this whole thing remains invariant under that. So I can do that. And if I do that, then I'll just rub it here and I'll change it to bk here and minus k here. So that's the only thing that changes. But every other thing remains, sorry, let me write it more carefully. This remains as plus because I changed only the level on the B oscillators. So that's what I get, okay? So as an exercise, if you are not convinced, you can show that this remains invariant under this relabeling of k to minus k, okay? And that's why you are allowed to do that. Now, in the, yes, when you are dealing with the real scalar field, so if when you do the exercise on the real scalar field, there you will have a relation that this B oscillators that we are writing is actually the conjugate of A star. But in the complex scalar field case, there exist no such relations because they are all independent oscillators, okay? And the way to check that is, so you see, I wrote down an equation for phi. There will also be an equation for phi star, okay? That will be the momentum version of phi star in the complex phi tilde star, momentum analog of the phi star in the complex scalar field case. So there was an exercise where you would have derived the equation of motion for the complex scalar field, and you would have gotten two sets of motions, one for phi and phi star. So you can treat independent phi and phi star of each other. And hence you get two sets of oscillators, A and B, with no such relations, which otherwise you would have expected in the real case. So that's why A and B don't share such a relation here. Okay, that's true. Now let's define the canonical momenta of phi is del L del phi dot, and this is going to be this, and phi pi star is del L by del phi dot star, which is phi dot, okay? And let me call this quantity pi and this quantity as pi star, okay, for simplicity, because this is the canonical conjugate of phi, this is the canonical conjugate of phi star, hence the notation, okay? Now with this, we can write down the Hamiltonian, which will be pi dot plus phi star uh, pi dot star minus L, the Legendre transform of the Lagrangian. So this will turn out to be this quantity del phi star del phi plus m square phi star phi, okay? So till now we are just writing fields. Now we will promote them to operators. Okay, till now again everything was classical, but now we promote them to operators. So promoting means you just give them hats. Okay, that's what we learned in classical mechanics, right? And conjugates will translate to uh, transjugate. Okay, so this was a like transpose and conjugate, because this would be matrices in some cases and so on and so forth. And similarly the pi's, the momentas and the pi stars. Okay, so that's why we have a dagger here. Okay, the conjugate maps to the transjugate, just as you do in quantum mechanics. So this means now we can write down directly the operator version of what we wrote as the position space phi, but now an operator. And because you have done preschool, I think, on simple harmonic oscillator, So we know that these ladder operators can also are at the end of the day they are operators. So we are allowed to just promote everything with a hat. Okay, right. So B will now turn to be dagger, and if you don't yes, so I'll be uploading my lecture notes, yeah, after the class, yeah. So we get this. Sorry for being a bit slow. These indices and plus and minuses are yeah, they're quite bothersome. So we just promoted A and B to operators because we know from our study of harmonic oscillators that we can expand the coefficients of the plane wave basis to operators, which becomes your ladder operators of creation. And similarly, we can write down the Hermitian conjugate as this. Sorry for the disturbance. Yeah. So the Hermitian conjugate is going to be exactly the same, but with daggers and eyes in the right places. So let's say there's a dagger here, there's a plus I now here, and then this now doesn't have a dagger and a minus. Okay. So this is again just simple harmonic oscillators, but done more rigorously for operator valued fields. And similarly, you can write down pi hat xt as pi hat dagger xt. So let me write that down again. D3k omega k by 2. So you see what's happening is because of the time derivative, this I omega comes out, and that's why you get an extra I here, and you get an overall omega here, and so you get a omega in the numerator under square root. Okay, so that's what is going on. It's again extremely straightforward but tedious. So you have to do it once very carefully. I still get confused, so it takes a bit of time to get all the signs correct. And then you get a minus because of the minus here. So you get minus bk hat e minus I omega t plus I k dot x. Okay. And similarly, you can write down pi hat dagger. Okay. So I'm not writing the expression, but you get the idea. Okay. So once you write that, now let us impose the commutation relations. Okay. So let's see. Yes. So now we will impose the commutation relations that phi hat, pi hat. So I'm suppressing the space-time dependence. Pi hat dagger, pi hat dagger are satisfy this non-trivial commutation relation. Okay. And rest all are 0. So this x and y are here, okay, in the space part. So as I said, I am suppressing them for notational simplicity. Okay. So now let's see what happens when we impose these relations. Okay. So recall that in the quantum mechanics case, when you imposed this thing as I, what you got was a dagger was identity, right? So we will see that something similar comes about here also. Okay. And that will be a commutation relations involving these oscillators A and B's. So let's do that. So before that, we will also recall another fact. So recall that the Fourier transform of just identity is the delta function. Okay. Again, this is something you can show. So what do I mean by that? It is this identity. E to the power ip dot x is 2 pi cube delta 3p. Okay. So here is the identity function. So imagine it as 1. So the Fourier transform of that is just the delta. Okay. Right. And it's very easy to see from the definition of the delta function, right? Now we consider equation, this thing, let me call it star 13, this is star 14, star 15, and this is star 16. Okay, so what we want to do is now multiply star 14, sorry, so star 13. So we multiply star 13 by e to the power I k dot x, and then integrate over all x. Okay, so what we want to do is this t3x e I k dot x and phi hat x t. Okay, so when we do that, what we get, so this again you have to do very carefully since this is the first time. So let me do it. So I'm calling it k prime now. A k prime e to the power minus I omega k prime t plus I k plus k prime dot x. I might leave out some vector signs here and there, but you will get it from the context. Okay. But again, in the lecture notes, the typed lecture notes, which I will upload in the Slack, all the signs will be there. So you can see and try to see if I have missed out certain things. Okay. Plus I k minus k prime dot x. Okay. And this now you can simplify to d3k. Sorry, I missed a factor of 2 omega k. So this will be simplified to 2 omega k prime square root a hat. Sorry, again, I will be missing hats here and there. So please bear with me. Sorry for that. 2 pi q del 3 k plus k prime. But we will, after doing this tedious computation, we will look at the structure. Okay, the structure will reveal something nice. Prime t 2 pi q, again another three-dimensional delta k minus k prime. Okay, and then there's a bracket, right? So again, if you don't are not able to read it in real time, it will there be in the notes, and just doing Fourier transforms, position to momentum space and vice versa very carefully. Okay, so that now we can evaluate these deltas. Okay. So I can just tell you that going from here to here was using this identity. So we used the identity to get rid of the spatial integral, and that identity, that's why I gave these delta functions, just like here that a special integral gave delta functions in the momentum. So here also doing the special integral gave delta functions in the k space or the momentum space. And now we can do the integral of the momentum space using the momentum delta functions. So when we do that, what we get is this thing, okay? We get d3x e to the power I k dot x phi hat x t equals 1 by 2 omega k a hat minus k e to the power minus I omega k t plus b hat dagger k e to the power plus I omega k t. Okay. And if we do a similar thing for the pi dagger, we get this equation. Okay. If we do a similar thing for pi dagger, again, I apologize, it's a bit tedious, but just bear with me. B dagger k e plus I omega k t. Okay. Now, notice using these two equations, this equation and this equation, you can multiply and add and subtract to write down these commutators in terms of phi and pi. So you can invert them. Okay. So that's what we will do now. And if you do that, you get a hat. So before doing that, you can do something. You can relabel here. So you do a careful relabeling of k going to minus k for the A oscillators. And similarly, you change wherever it appears. Okay. Only one thing to note is that under this relabeling, the energy will still remain the same. Okay, because remember that it was mod of k square m square. So k to minus k doesn't change this. So with that in mind, if you now write down the oscillators in terms the ladder operators in terms of the fields, the operator valued fields, you get this quantity. Okay. D3x e to the power. So I will schematically not write this. I will just write the general structure that will be helpful to us. Okay. So phi omega k over 2 plus I pi dagger 1 over 2 omega k. Okay. And so I am suppressing space-time dependence here. Okay. Just for notational simplicity. Also, I'm not writing this explicitly, but if you want just for this particular A, let me write it down, but I will not write it for the other A's and B's. Maybe you missed a dagger in the previous equation. Yeah, it could very well be. Let me see. Yes, there's a dagger here. Thank you for pointing out. Yeah, so I might be missing out those daggers. I'll try to be careful. But okay, let me now write down A and B dagger. So B dagger again is this integral. I will not write, but the main thing is the structure. So we will just write that. Again, pi dagger 1 by 2 omega k. Okay. And now if we write down A dagger, you get phi dagger. Again, the same omega k by root 2 minus I pi hat. I'm missing hats, but okay. And B bk will be similarly phi dagger omega k by 2 plus I pi 1 by 2 omega k. Okay, so this is the structure that I was talking about. Let me zoom out a bit so that you can see all the four together. So A is given as phi plus I pi, B dagger is phi minus I pi dagger, A dagger is phi dagger minus I pi, and B is phi plus I pi. Sorry, I again missed some things. Yeah. So phi dagger and minus I pi. Let me just check once if it's correct. Phi minus I pi dagger, phi plus I pi. Yeah. So the way to remember is you will always have phi and pi dagger in combinations and plus and minuses. Okay. They will never be phi and pi and pi dagger and phi dagger. So that's a consistency check. Okay. Now it's straightforward. So now what we want to do is we want to compute this quantity AK and A dagger K prime. Okay. So we want to compute this. So for that, what do we want to have a look at? So let's define this K prime instead of K now. So now we want to look at this operator and this operator, right? Yes, so those are the two operators we want to look at, and you see what it will give you. It will give you, if you want this commutator, it will give you phi and phi dagger, and then phi and pi. Okay, then it will give you, so with a minus sign, minus I, then it will give you plus I, pi dagger and phi dagger. And remember to respect the ordering because these are operators like matrices, so they don't commute. And the last thing is plus pi dagger and pi. Okay. So let me now check if that's the correct structure. So schematically, this is what you get, and there are integrals. But this is the structure you should be aiming for: phi dagger, phi pi, phi dagger, and pi dagger pi. Okay. And there will be some factors of these square roots, omega prime, and omega over omega prime in some cases. Okay. So if you are careful enough with all that, what you will finally get. So here, so once you write this way, now you can impose at this stage, impose the commutation relations. Okay. So if you impose the commutation relations, these are these relations. Let me go back a bit. Yeah, these relations. So star 12. So if you impose star 12, then you will get nice delta functions and zeros here and there. For instance, this and this will give you zeros, and this and this will give you deltas. This and this will give you deltas, and this will give you zeros. So using that, you can now write down a k, a dagger k prime equals half 2 pi q delta 3 k minus k prime e to the power I omega k minus omega k prime t. And then there are these factors omega k by omega k prime plus omega k prime by omega k. So I hope the general idea is clear that what we did. So with that, we get this. Now you see that we have a delta function multiplied here. So we can take k to k prime to get rid of, we can take k to k prime to collapse this to just 1 plus 1, okay? Because if k is k prime, they're equal and they're all multiplying a delta. So if we do that, what we finally get is this 2 pi cube delta k minus k prime, okay? So this says that just as we had in the simple harmonic oscillator, that this relation that generalizes in the operator valued field case to a commutation relations like this, okay? And if you do this, you can show that yeah, this is what we get. Now that is, so when the ladder operators that we constructed in this case, they satisfy this relation, we say that we have quantized our system. And now let's see what happens when you act it on vacuum and things like that, okay? Good. So yeah, so let's look at the Hamiltonian in that case. Okay. So now the Hamiltonian, note that if we promote it to operators, it becomes like this. I had dagger, which is exactly the field theory one, but now with hats and daggers, m square phi dagger phi, okay? So now you can do, so because you know all of these pi's in terms of these operators a and a dagger, sorry, these operators. So you use these commutations and you can show that you can write this in the momentum space as like this. A k dagger A and B hat K, B dagger K. Okay. You didn't write bar initially. Only K bar is present. No, sorry, that's not a bar. So, okay. So when I'm writing this, I mean this. Okay, so it's like a, yeah, it's like my notation for a vector. So K bar denotes vector K. Okay, so it's not conjugate. Yeah, I should have cleared that out before, but okay. So that's a notation. So these are three vectors, these quantities, okay? Like in the truest sense, they should come with an arrow. Now, yeah, you can show that the Hamiltonian looks like this. But now, if you use the commutation, then you can write this in this way too. Again, let me just write it schematically. So B dagger B plus 2 pi q delta 3 at 0. Okay, because that's what you get. Yes, there was a good question. I somehow missed it at first about didn't we just use the delta function? Very good. So you see that here there was this factor, and I said that we had a delta function here. So using that, we can set it to just 2, which will cancel this 2 here. And when you do that, you actually get a delta of 0 here. Sorry, here I did a mistake. It should be k prime, a delta of 0 here. And that is when you have, when you are looking at the same modes. So if you do this, then instead you have just the delta of 0. But otherwise, if you have a different mode, then you get a k minus k prime. Okay. So that's why I said that using this delta function, we can say that when k is equals k prime, when that they both boil down to just 1 and 1. But in another way of writing, you can set k prime to k here, and that just says that you're evaluating delta at 0, which is exactly what we are using now to write b and b dagger in terms of b dagger b plus this 0. So that allowed me to set this to 1. Okay. So so now you see that now we have a problem in the Hamiltonian. The problem is if you if you take the Hamiltonian and act it on the vacuum, which is 0, and I will define what is 0 as the one that is annihilated by all the A's and the B's oscillators, okay, for all K. So now if you do this on the vacuum, so these things are fine because they have a annihilator operator on the right, but this object survives, okay, this doesn't kill the vacuum. So you get an integration like this: omega k 2 pi q and delta 0 acting on the vacuum. Okay. Now this is a bit bad in the sense that this blows up to infinity. Okay. Because of this delta function over here. So this quantity, this actually diverges. Okay. But you see that that was expected. This is not bad from the point of view that this implies that now we are observing the infinite degrees of freedom of fields that we started with. So the problem is that since we had fields, we had infinite set of harmonic oscillators. Okay. So because we had infinite set of harmonic oscillators, so note that each harmonic oscillator gives you an energy like omega. Okay. But now we have that same omega, but an infinite integral uh, in the momentum space. So imagine like summing over this omega like for the infinite set of oscillators, and that is because they are describing what are fields. Okay. So because of that, you get this infinity. Okay. So this is exactly the 0 point or the vacuum energy of the oscillator, and it is just a manifestation of the infinite degrees of freedom of the fields. So one way to navigate this is to define what is called a normal ordering prescription. Okay. Because you see, even though this is infinite, at the end of the day, you can only measure energy differences, okay, not absolute energies. So that's why in energy differences, you will at every level you will have this infinite contribution, but when you take the difference, these infinites will cancel among themselves. Okay. Just like in the simple harmonic oscillator case. So the 0 point energy now contributes an infinite energy here. So that's why we can just neglect this. We can treat this as a reference that all we want to measure is on top of this infinite 0 point energy. So that's the prescription of normal ordering. So normal ordering says that let's look at it with this example of Hamiltonian. So it says that you define your Hamiltonian in such a way that you always write the annihilation operators to the right of your creation operators. Okay. So which is essentially saying that you neglect the 0 point energy. So it's just that I dropped this quantity altogether. So normal ordering tells me that if you write objects in such a way, operator valued fields in such a way that all the annihilation operators are to the right of all the creation operators, then that amounts to saying that you neglected the 0 point energy. And at the end of the day, when you compute something in the lab or you do a physical calculation, you only are interested in differences. No absolute energies ever is computed. So now if you add this object on the vacuum, which is annihilated by all the fields, then this just give you 0. So the vacuum indeed has 0 energy now in using this prescription. Okay. Okay. That's fine. Yeah. So uh, that's true. That's okay. Now let's yeah. So that's the idea behind normal ordering. Now let's look at single particle states and see how we will build in particles now. Again, this will be analogous to the oscillator, the simple harmonic oscillator you learned in quantum mechanics. So if you compute H, this normal ordered H and a dagger of K. So this is like computing this quantity, commutator of this quantity. So T3 K prime by 2 pi cube omega K prime, a dagger K prime, a K prime, uh, and a dagger. Okay. So when we compute this quantity, uh, and there's this B piece, okay, B dagger B. So when you compute this quantity, you will get that you get this to be omega K, a K dagger, okay, and yes, if you do that with the A, then you get minus omega K A K. Okay. So you see that this is like you are creating, sorry, isn't this normal ordering change particle? Sorry, I don't understand the question very well. Yeah. So if you do this, you get this quantity, and now if you do this for the B, for the B's, you get exactly the same relation. Again, this which you should carefully work out. Minus omega K pk. Okay. So this means that if we act on a state with this, you can show that you will get an energy of omega K, where this omega is the one we had seen, K square plus M square. Okay. And similarly for the B. So this means that we have created a particle. So this states AK dagger 0 is a particle, but in momentum space. Okay, that is crucial. This is not a particle in position space with momentum K and energy omega K. Okay, so this is again properly justifying that the T00 that we defined as like this quantity that we defined as the Hamiltonian is indeed the energy. Okay, now we see that. Okay, so I'll just take 5 more minutes for this class and then I'll stop for today. Yeah, so let's see. that does this thing. Right. So yes, what did I have to say more? Again, these are the things which you can check out as exercises. Some of them will be worked out explicitly in the lecture notes. Okay, let me think. Do I need to discuss that now? No. Okay. So next time we will discuss what are the symmetries of the complex scalar field. So next time we will start with the symmetries. Sorry, I was a bit slow today. So symmetries of the complex scalar field. And we will see that the charge that we will construct from here will commute with the Hamiltonian. And we will discuss about antiparticles and all those things, how they come about. Okay, so let me end this section, this lecture today here. Sorry, this should be just A and A dagger. Yeah, so you see that what we did today when we took the complex scalar field and we quantized it, we saw that these creation and annihilation operators that we got, they satisfied a similar relation like in the simple harmonic oscillator case, but generalized to operators, and hence you get these delta functions there in the commutations. And another thing we saw is that they indeed create particles on when acted on the vacuum with momentum k and energy omega k. Just like in the simple harmonic oscillator case, you had energy as omega. But the only difference is in the simple harmonic oscillator, those were excitations in the position space. But here, these are excitations in the momentum space, because we started with taking the scalar field Lagrangian and then writing it in momentum space, which gave us this added benefit that it now became a set of decoupled oscillators, but in the momentum space. So excitations will be localized in the momentum space. Okay. You see, whenever you will quantize from now on, like when you quantize the vector field, so we will quantize fermions in next week. We will see that at the end of the day, it will be an infinite set of oscillators writing down commutation relations, and at the end, doing this procedure that we did today. So in some sense, this is why people say that uh, not people. There was this great physicist Sidney Coleman who once said that a career of a young theoretical physicist is understanding simple harmonic oscillators at different level of abstraction. Like you had a course on simple harmonic oscillators, but now we treated fields as a collection of simple harmonic oscillators. Okay. Uh, and the other thing I want you to take home is normally calculations in QFT are easier in the momentum space. As we saw that modes decouple in the sense that each mode has its own differential equation to satisfy, its own set of oscillators and commutation rules. But in position space, at times they could be highly like interacting and strongly coupled. But when you go to momentum space, most of the times they become decoupled, like here. So that's why, there is this slogan that you try to visualize and think the problem in position space because that's easy, but then you compute things in momentum space. In fact, when you will do interacting quantum field theory, you will write down what are called Feynman diagrams. You will realize that the momentum space Feynman diagrams will be much easier compared to the position space. But position space is obviously more natural to think, but to do computations, this is easier. Yeah, and yeah, I think that's it. Again, I'm sorry because the last part was a bit dry, and maybe I did some errors somewhere with K's and K primes and some hats and not hats here and there. So bear with me. As I said, you can ask things in the Slack after the lectures, and I will try to correct the errors that are there if I did commit any errors. But as much as possible, the lecture notes will be quite true, and they will not be containing errors. But if you find, do let me know, And if you get stuck anywhere, again, keep asking questions in the Slack. Whenever I get that time, I'll look at it. But uh, again, the final message is this is exactly the simple harmonic oscillator that you did in the preschool, but doing it in a more abstract and with more continuous parameters, fields, and these kind of things. And coming back to someone's question on the quantization, so as I said, we are not defining what is quantization. We took what we know quantization means from classical physics. That is, instead of Poisson bracket, you impose commutators, and we are doing the same thing for fields. Okay. At no point am I saying that this is exactly what quantization means, but this is one way to quantize. And at the end, you saw that actually we are able to create discrete packets of local momenta. In the momentum space, we are able to create discrete packets omega k of energy. So we indeed quantize the field of the complex scalar. Okay. So that's why this is one process of quantization. And we are told that when you take Poisson bracket, impose commutator relations, you get quantization. Okay, but as I said, I wanted to say something here. Now, people who are familiar with okay, so the question is this. Okay, let me phrase it this way. For instance, as far as I know, there is no way starting from a classical theory you can derive the Schrodinger equation. Okay, what you can do is people might claim that there is some derivation, but at some point you will like mysteriously hide in h bars and i's here and there, and you may not know. But at the end of the day, there is no way to go from classical physics rigorously, as far as I know, and end up with Schrodinger equation. At best, what you can do, because of this Poisson bracket and commutator structure, you can write down what is called a Hamilton-Jacobi formalism. For people who don't know, please bear with me. This is an aside comment. There's something called an Hamilton-Jacobi formalism in classical mechanics, and you can show that the Hamilton-Jacobi equation look very analogous to what the Schrodinger equation looks like up to factors of I and h bar. So you can just see some patterns emerging from the Hamilton-Jacobi to the Schrodinger. And the reason that emerges is because Hamilton-Jacobi is written in phase space, where these Poisson brackets are the natural players. So in the phase space, you have some symplectic structure, which is this commutator-like structure, but with Poisson brackets like PQ minus QP. So that symplectic structure is analogous to the commutator structure like AB minus BA. Okay. And why do we do commutators in quantum mechanics? It should be clear by now because we are dealing with linear operators. The whole section on group theory and Lie algebra was because quantum mechanics is done on a Hilbert space, which is a linear vector space. So that means you will generalize functions to linear maps, and commutators is what gives you the Lie algebra structure there. But that's the best I can do at the moment because, as I said, there's no rigorous way to go from classical mechanics and derive Schrodinger equation. So there is, so if you like this is a motivation, then that's a motivation for you. But yeah, okay. Are there any doubts? So maybe for a couple of minutes, I can take a few doubts, and then the rest we can discuss over Slack. Thank you. Thank you again for being very patient with me. Uh,
Thank you, Arpit. I think I'll turn off recording for now. Let
yeah,
them
yeah.
ask the questions. Yeah.
Sure, sure, sure. Yeah.